Hey everybody. In this video, I'd like to introduce you to one of the fundamental building blocks of today's AI. AIs are built on this fancy architecture called a neural network. A neural network is itself just a network of neurons. So today we're going to look in depth at what a neuron is. And the idea was, when you're trying to establish the field of artificial intelligence, those guys in the 1940s and 50s, they're like, well, how do you build something intelligent? Well, humans are intelligent. What makes us intelligent? Our brains. All right. Well, then what are our brains made out of? Neurons. All right. So let's use that as our launching off place, our starting place. Let's figure out how we can use the basic idea of a neuron and then put these all together and try to see if we can't create an artificial brain that is hopefully intelligent. So this is the idea that McCulloch and Pitts in 1943 kind of ran with. They were kind of coming at things from a biological and psychological perspective, and they were studying neurons. They said, well, let's just think of an abstraction of a neuron. I mean, a neuron, well, first let's just look at the biology of a neuron. A neuron, hopefully you remember this from biology. You've got this cell body, and you've got some inputs here. These little things that kind of stick out. My drawing is horrible here. And then you got the cell body for the neuron. You got this long thing called a dendron or something like that. No, that's the axon. And these are the dendrons, I think. And then there's some other stuff that sticks out of there. And so this is in general just a horrible drawing of a neuron. And these neurons kind of form a chain. So there's going to be another neuron here with its own axon and a bunch of little dendrons, and then and one of these little guys, and so forth. So again, dot on this. But how does this neuron work? What's going on in here? Well, the idea is that there's some inputs, some kind of electrical signals that kind of stimulate these little feelers on the left-hand side of this picture. And they load up the body of the neuron, kind of with this electricity, basically. And the instant that there's enough electricity that's loaded up into this guy here, it just can't contain its excitement anymore, and it fires. It shoots off an electrical signal. So it basically collects a bunch of inputs and then spits out an output. That output goes down the axon, and then essentially it forms an input into the next neuron. And there's going to be another neighboring neuron, and it fires too, and it maybe feeds into this neuron. And maybe there's another neuron also in the neighborhood. It got stimulated, and it shoots off its electrical discharge there, and that becomes the input. Again, and all these guys kind of load up their electricity into this next stage neuron, and as soon as it gets enough, electrical excitement there, then it also fires. And so there's this cascade of electrical signals that kind of propagate through the brain, neuron to neuron. All right, so McCulloch and Pitt said, all right, here's where the action is. Let's let's model this guy. At its core, what's going on? We have inputs, and we're going to get outputs. Right, those inputs are going on here, and then the output is what goes out of that neuron. So neuron is really just a mathematical function. A function, remember, f of x, takes some inputs, the x's, it processes them somehow, and it spits out an output right there. So really, the task now for the computer scientists, the brand new artificial intelligence dudes, to just have a proper mathematical function that takes inputs and gives you outputs, and in a similar kind of way that's going on with neurons. All right, so let's see how they did that. I'm going to erase my screen and meet you back here in a second. Okay, so let's look at a very simple neuron then. We're going to have the neuronal body here, and let's just have two inputs. And just for the sake of concreteness, let's just say we're trying to create a neuron that'll tell us whether you find someone attractive or not. So we have like this electrical stimulation of your neurons, and you're like, ooh, this person's attractive. Now, what are two things that we might find attractive? Maybe looks, and maybe intelligence. Right? And you get both of those things, our neurons get excited. All right, so we look out in the world and we see someone and they're like, ooh, they look hot. And then we talk to them and they're like, wow, they're intelligent. And if they're like pretty enough and they're intelligent enough, then our neuron gets excited, and it has an electrical signal, an output that says, yes, that's a 10 out of 10. That's a 100%. All right, so we have our inputs. Let's call these x's. So this could be x1. This could be x2. And these are going to feed into this body of the neuron, and then we're going to get out a y. All right, now still don't know quite what this function is. In fact, the function is going to be, we're going to split it up into two little smaller functions. It's going to be a little bit easier for us to digest this way. We could write it as one complex function, but let's just split it up. I think it'll be easier. What I'm going to do is take my x's, x1 and x2, and add them up. And we'll get something else. We'll get, let's say, this z, just to make up a letter. So there's this linear part. And then we're going to have a nonlinear part. That's called an activation function. And the simplest activation function is a step function. Basically an indicator of whether something has a particular property or not. And so that linear activation is basically going to say if z is positive, then our output should be a 1. And if z is negative, let's just make that a strict inequality, then this person is not attractive, not hot to us. So here we would have hot, and here we would have not. All right. Now I did skip one small step. Maybe you're a shallow person and you care more about looks than intelligence. Or hopefully the other way around. Hopefully you care more about what's inside a person than the surface features. But really all of us have different preferences. So one person's neuron might be a little bit different from another person's neuron. We weigh these attributes, these inputs, differently, you and I. So we need to kind of specify here in this model, like how important is looks and how important is intelligence. So let's take these inputs and let's multiply them by a weight. Each one gets multiplied by a weight, which we'll denote there with a W. And those W's are weights. And I'll put them here, W1 and W2 for weights. Well, gosh, this thing looks like a straight line. That's why we called it a linear function, right? A straight line, back from high school, was mx with some b here. If we just turn this m upside down, it looks like a w. And that's really similar to at least this part here. We just called that a z. That was arbitrary. You know, this thing could have been a z. It doesn't change anything but a label. The only thing that's different, well, there's two things. Here I've got two inputs, so we could have added a second linear input and then flip that upside down and had our x. Change our m's to w's, flip it. The other thing that's missing is this intercept, because, you know, like in high school, there was always an intercept. And we could add that into this model also very easily. We'll do that right there. Just add a constant. In other words, maybe you're hard to please no matter how, you know, attractive and intelligent a person is. And so this thing would be a very small number. Making it hard for Z to get excited enough, large enough for your neurons to fire. Or heck, maybe you're easily impressed, or you don't date much, and so your standards are very low, and maybe that B is also quite low for you. Maybe it's a 0. Heck, maybe it's negative. And so that it's super duper easy for your neurons to get excited. You can see how these parameters, these W's and these B's, can kind of describe your dating preferences, right? They describe how important different features are, and then also how easy you are to excite. And all of that is captured in this linear function, this straight line thing. We just had these W's and these B's, and that gives us a lot of information. By the way, I should mention that this B here is called a bias. And then again, these guys, let's just write it down here. That's a weight. And this is another weight. And these weights and biases, these are called parameters. So these weights and biases, these are the parameters of the neuron. Now, I haven't told you where these come from. They're just, at this point, we're just going to say that they're there and they describe your dating preferences. Okay, so I think we have all of the pieces now of a neuron. Let's just quickly summarize. We look at a person and we talk to the person and we say, wow, they're really pretty. This value for prettiness, maybe it's a high number. Maybe they're, well, let's work out an example. Let's just say that this person that we're looking at, very pretty, 9 out of 10. And let's say that you talk to them and they're of, average intelligence. Let's say they're a 5 out of 10. Now, what about the weights? Let's just suppose that looks are not very important to you, so that the weight attached to prettiness is a 1. And the weight attached to intelligence is, let's make up another number. Let's say it's an 8. So intelligence is 8 times more important to you than looks. All right, one more thing we need. We need that bias term. We're going to just make up a number. Again, let's just say it is a 10. So let's see if, given our preferences, our psychological preferences, and this particular person's attributes, whether these two together can make our neuron fire. All right, well, we need to feed these into the linear part, then feed that linear part into the nonlinear part, and then see what happens. All right, so let's start plugging in values, in for the W's, the X's, and the B's. So we have W1, let me just write this out again, W1, X1, W2, X2, plus the bias, is equal to something. So what's W1? W1 was a 1. X1 is a 9. X2 was a 5. W2 is an 8. X2 is a 5. The bias is a 10. And we just need to figure out what that Z is. All right, so what do we got here? We have 9 plus 40 plus 10 is equal to Z. And so what is that? That's 40, 50, 59 is equal to Z. So that's what comes out of this first part, this linear part. Then we need the nonlinear activation function. In other words, this part here. To see that last step to see whether we find if our psychology, when confronted with this particular person, whether that combo means we find them hot or not. So, all right. So I'm running out of space here. Let me let's block off some stuff. So, you know. All right. And so we had 59 is equal to Z. Well, let's see. Is Z greater than 0? Yeah, it's 59. So it's pretty high. So all right. So that means since 59 is greater than 0, then Y is equal to 1. And we find this person very attractive. Or at least attractive. It's a binary thing. It's hot or not here. All right. So cool. We've got like this very simple mathematical model of your dating preferences. Not bad for like basically a straight line and a step function. Now, we're going to see in a later video that the simple perceptron model, what I just drew up on this one screen here, this line and activation, can describe a lot of logical functions. And one of the prereqs for intelligence is at least to be logical. So we'll see in the next video that the neuron can mimic logical functions like and. Like maybe I need someone to not just be pretty or intelligent, but pretty and intelligent. So we can do ands, we can do ors, we can do nots, just with a single neuron. That's pretty cool. Then we'll see that there are some logical functions that we can't do with a single neuron. It's going to take more than a single neuron. It might take a couple of neurons, maybe even a network of neurons to mimic complex logical behavior. All right, we'll save that for the next video. Thanks for your attention.